We're going to move into Chapter 8 and look at real numbers and algebraic thinking. When we talk about real numbers, students often say, well, what does real mean? There are such a thing as imaginary numbers, so it's good to introduce students and say that there is something that is not real. We're just not quite there yet. Real numbers are a group of rational numbers. So rational numbers falls under the umbrella of real numbers, and they can be either repeating or non-repeating decimals. They are going to be terminating decimals. It was the ancient Greeks who discovered that numbers that are non-terminating and non-repeating decimals, those numbers are typically called irrational numbers. Characteristics of irrational numbers are there's an infinite number of digits on the right-hand side or behind the decimal point, and there can be repeating blocks of digits when we have irrational numbers. Irrational also falls under the umbrella of real numbers. Irrational numbers happen a lot with square roots. So when we're solving for the dimensions of a square, the area of a square would be the side times the side, or side squared. To find that actual side value, we would be taking the square root of something. And when we do the square root of something, that can wind up putting us into one of those irrational categories. So alternately, if we know the area, we can also take that, square root it, and find the length of the side. However, it's important to talk about the fact that a lot of times this rule gets stated by math teachers that the square root of something is always positive or negative, but that's not true in this case because a square can't have a negative length. So we want to be careful how we word that portion of the square root discussion. Square roots are going to be a square root of a non-negative number is going to be some number so that when you square it, you get the value back for a. A principal square root is if a is a non-negative number, the principal square root of a would just be shown as the square root symbol of a, and it's going to be just the non-negative number. So if I'm looking for the square roots of 144, that would be negative 12 and 12. I don't have any context here that tells me it's something where I can't include the negative number. The principal square root of 144 is 12. So when we talk about principal roots, we're talking about the positive one. In C, when I have the square root of a fraction, I take the square root of the top and the square root of the bottom, and that would give me 2/3. We can also take an infinite number of roots. I could take a cube root, I could take a fourth root, a fifth root, a sixth root. And when we start getting beyond square roots, that's where we have this value n that we fill in. If n is even, then I'm going to have a positive root. If n is even and x is negative, then it's going to be not a real number. If the n value is odd and x is negative, so the cube root of negative 8 would be a negative answer. Only negative, not negative and positive. So some square roots are rational and some are irrational. So when I take the square root of, say, 25, that just gives me 5. 5 is a rational number. It can be expressed as a fraction. But if I have the square root of 2, that's going to be an irrational number because there's no way that I can put that square root of 2, that actual decimal value that you get out of it, into a fraction. So that's going to be the problem there. One way to show that it's irrational could be something called an indirect reasoning proof. This is for your higher level elementary education students. So we're going to say, assume there's some rational number such that when I square it, I get 2. Then if that's true, then I must be able to do a squared over b squared is 2, and then I would multiply both sides by b squared. But by the fundamental theorem of arithmetic, the prime factorizations of those two values are going to be the same. So this means that the prime 2 appears the same number of times in the prime factorization of a squared as it does in 2 times b squared. So this is just kind of taking you through that proof process. Of course, this is not something we're going to show all of our students, but it is important to recognize what is happening and the thought process here. So the thought process basically happens to where you get a contradiction. So you're going through the algebra of this process, and then it's like, wait, something's not adding up. So that happens in this last step. The contradiction, when you're doing these proofs by contradiction, could have been caused by the assumption that the square root of 2 is a rational number. So that assumption there could have made our line of reasoning invalid. So then we must say that it can be an irrational number because I've contradicted the idea that it is rational. Here I have a figure and it's going to be kind of on this number line. I have a triangle basically. And it's got a segment that's 1 unit long and it's perpendicular to that number line. That's what that little red box means. So if that's true, and I'm looking at the number line, then the height of this triangle is 1. The width of this triangle is 1. So the two sides of the triangle are going to be 1 unit long, but the hypotenuse would be 1 squared plus 1 squared. So I take the square root of that, and that would be the square root of 2. So I can find that point Q by making an arc with a center of 0 and a radius of C, which would be the square root of 2. Other square roots could also be constructed with similar ideas utilizing triangles. So I could utilize the two sides of a triangle to get to a root. If I want to estimate a root, it's typically something that we can say, it's going to fall between these two numbers. So the square root of 25, you could say something theoretically and say it could be between 4 and 6. So we're going to kind of squeeze these irrational roots between two numbers. So once I get to something like, say, the square root of 7, the square root of 7, because 3 squared is 9 and 2 squared is 4, then the square root of 7 is going to fall somewhere between those two values. So you see we're squeezing these actual values here. Now the set of real numbers, so again, real is that big umbrella, and it's going to have rational and irrational numbers underneath it. So real is kind of like the big blanket. It's going to really include a lot of different things in it. The decimal form of any real number is terminating, repeating, or non-repeating. So at that point, I'm kind of encompassing everybody when I say this. So real is kind of like the big idea in math. So integers would be real numbers then, rational numbers are going to be real numbers then. So if you're looking at this, this is kind of just showing you the visual for the umbrella. If I've got the umbrella of real numbers, irrational number and rational numbers fall underneath it. Then rational numbers can be divided up into further subgroups with integers, whole numbers, and natural numbers falling under that umbrella as well. We've talked a lot about closure properties. For real numbers, if I add them or I multiply them together, the answer is going to be a real number. For the commutative, it's also going to be true. The commutative property is going to be true when I deal with real numbers, and so is the associative property. Excuse me. The identity properties are going to hold true for real numbers as well, so we're not going to have any restrictions there. The inverse property will also hold with real numbers. So all of these properties that we've seen to date are going to hold under the umbrella of real numbers, which should make sense because if it works for an integer falls under the umbrella of a real number. So then my real numbers would also have to fall under it. This is just a reminder for notation, and a lot of times we struggle with notation in math because there's so many different ways to show something. So what we're showing here is that a root can actually be written as a fractional exponent. So if I was doing the square root, that would be 1 divided by 2 as my exponent. Or I could show it as the square root of x. Now I don't write a 2, but in that little check mark area because it's assumed. So we're kind of assuming that it's always going to be a 2. If it's anything other than a 2, I would actually write it in there. And then we have, when we actually have a variable in the top of the fraction, that affects the exponent under the root. So there's some more properties of exponents there. I've shared a couple of videos with that. If you want to go on my YouTube channel, you can pull up exponents and it's going to give you a lot of work with the properties of exponents. If you just need a little refresher on that, please feel free to do so. Here are some examples. We're going to move through them a little quickly because, so again, if you need to review the exponent rules, you can definitely do that. So if I have 16 to the 1/4, that would be the 4th root of 16. You could use your calculator and you'll type in the button with the root on it with the x in the middle, and it would give you 2. If I had 16 to the 5/4 power, that would be the fourth root of 16 to the fifth. Since I know the fourth root of 16 is 2, I can simplify that as 2 to the fifth. Or I could type it straight in my calculator. Here, I'm going to have the cube root of -8, and from earlier, if we have the cube root, it's odd, of a negative number, the answer is going to be negative. And D, this is going to be an exponent property. When you have a negative exponent, you take the reciprocal of the number. So 5 to the third power becomes 1 over 5 to the third power. But when I take 1/3 of the cube root of 5 cubed, those are going to cancel out. And then the last one, because I have an even root, that 4 is even, I cannot take the root of a negative number and get a real number if the root is even.